We want to thank you very much for coming to the lecture today, in which we're going to talk about beyond what the eye can see, using technology of NASA's rovers to explore paintings. The lecture will be given by myself, John Delaney, and Kate Dooley. We're both in the scientific research department at the National Gallery here. So what I'm showing you on this slide here is sort of the typical images collected in all the sort of major museums around the world when you look and study paintings. Of course, you get a very nice high-resolution color image. You get an X-ray, which we're all familiar with. This is related to optical density of the materials. Usually things like lead white shows up. And then you get something called an infrared reflectogram, an image taken in the infrared. And in the infrared is the portion of light that's beyond the visible. So the range just beyond. Not the range where you start to really feel heat, but in the range that you can't see by eye. And essentially, in this range, you're able to get below the paint layer and see original sketch marks or drawings or other compositions. You can see there is a woman beneath this painting here by Pablo Picasso that is sort of been covered over by the painting of the boy here, Le Gourmet, who's eating out of this bowl. So as I said, these are currently the images taken today, and what we're going to talk to you today about is new images that are being taken to answer fundamental questions related to is the painting by the particular artist of interest, and how was it changed and what materials were used. Now, how do we actually look through a painting to see the underlayer of preparatory sketch? Well, the trick is we have to find a way to get through the upper layers of paint. This is a cross-section here taken from a painting showing paint layers, a ground layer, and then some black lines here, black material here, which is the underdrawing line, or the preparatory sketches. So to see through the upper paint layers, we have to take advantages of two effects. One is to minimize the absorbance. This equation here describes the transmission of the paint layer, which is basically proportional to scattering by the particles, pigment particles, and absorbance by the pigment particles. Two things happen when you go in the infrared, outside the visible. You get less absorbance. You also get less scattering. And scattering is an important component. Snow, for example, is white. Doesn't absorb any light. It only appears white to us simply by the scattering effect by itself. So it's a combination of scattering and absorbance to give rise to the color. And so when you have light coming into this notional paint layer, you have light lateraling around in the visible, picking up, being selectively absorbed and emerging out with a color change to it. But if you go into the infrared, we have light passing through, not being absorbed, minimizing the scattering, reflecting off the preparatory ground layer and up to the camera. Light, red light or infrared light that strikes an underdrawing line, which is preferentially absorbed more by compared to the white ground layer, it's absorbed and less light goes back into the camera, so we get a contrast difference. Well, this is a kind of a nice dramatic example you can show of why you can minimize light scattering by going to the infrared. And anybody who's gone to Los Angeles is very familiar with the fog, and especially the haze in the sky. This is a picture, a black and white picture, taken from the Painting Conservation Studio at the Getty. And you can see it's very hard to see the mountains in the distance in the visible due to the aerosol and smog in the air. But if we go to the near infrared, the same region we look through the paint layers in the paintings, you can see we can penetrate that atmosphere and we can see the mountains quite clearly, as well as a lot of the objects in the distance. So you can sort of think about the atmosphere in between as essentially being analogous to this paint layer of particles. So by going into the infrared, we minimize absorbance of light by the pigments and minimize the scattering. Well, when you do that and use that technology to look at paintings, you go from the color image to this infrared image. And the infrared image can give you a lot of information about changes in composition that the painter may have actually decided to make. In this case, he's essentially changed what would be a Romanesque church into a more contemporary to that time period. You can see a lot of drawing here, these arches and the like, that didn't make it into the final composition. These can be revealed. You can also see that Christ, this is a painting by Van Orley of Christ among the doctors. You can see that he's on a pedestal in the drawing, but that was not carried through the final painting. Now, when you look very closely, and when you bring these pictures in register, you can see, we can understand how all these little changes were made by the artist, and then how it was finally executed in paint. And one of the things that shows up kind of nice is if you look at this edge of the final painting of this arm, when he initially drew them, this arm was up much higher. And he decided to make this foreshortening or this correction for the final composition. And you can also see this fellow here has several noses, trying to get the right orientation right. Okay, so that's sort of a classical example of underdrawing. This is a painting I'm sure most of you are familiar with, painting by Leonardo da Vinci in the collection here, Ginevra. There is a tremendous amount of lead white which is used to make this incredibly lovely luminescent face. And underneath here, there will be some sort of drawing or preparatory sketch. And when we go to the infrared to make it rendered visible, we don't see drawings, right? We see actually individual dots. So this has essentially been transferred in a stenciling process, a pouncing process. Apparently he had made a sketch of the young woman and then pricked holes in it and then transferred it onto a white board that was probably still tacky with lead white. And you're seeing essentially the carbon dots left over. So this tells us quite a bit about that he didn't start drawing with a board. And for a curator and conservator, these type of images have a lot of meaning about how these paintings were prepared, when they were prepared, and some of the details in the painting process. Now, besides looking for drawings and preparatory sketches, we can also visualize some of these, what we're going to call painted compositional changes, that a painter decides to make changes to the composition. In this case, for Feast of the Gods, a painting that's been worked on by at least 3 painters, but certainly started by Bellini, finished by Titian, and maybe Dasso Dasso in the middle. And so there are a lot of compositional changes in these paintings, this painting that has occurred over time. By taking an image in the infrared, you can see quite clearly this hillside was originally a stand of trees. So the original composition consisted of a stand of trees with the gods in the foreground. At some point, this change was made. And my colleague Kate Dooley will talk more about what we can learn beyond just simply there was a stand of trees in the background. Now, what I've shown you so far is just taking pictures in the infrared, broad-banded, without actually worrying too much where we look. And what I want to try to show you in this slide is that by leveraging techniques that NASA has used for years, by taking different pictures in different spectral bands, we can see small differences that relate to materials. And that can give us more clues as to how the compositions were put together. So what we're going to do is look at 3 images taken where we swap out different filters in front of our camera. The painting here is Little Girl in a Blue Armchair by Mary Cassatt in the collection, a very lovely painting. And I'm essentially going to show you these stacked up like cards in a playing deck where we're going to go to longer wavelengths in the infrared. So there's our visible image. That's the first infrared image. Going a little further out, you can start to see a little differences, but they do look very, very similar in many ways. And then the third one. Well, if we put them all together in a stack, and you start to look and compare, you can start to see there's a little bit of an edge difference here going on. Well, looking at a lot of images side by side to look for subtle changes takes a lot of time. It's not very efficient, and you can miss things. So a technique that has been used for a long time is essentially called to make a false color image. So we're going to take those 3 images in the infrared and pretend we're going to make a color image out of them. We'll take one closest to the visible part of the infrared, visible range in the infrared, put in the blue gun, put the next one in the green gun in the red, and make this false, or what some people like to call artificial color image. And a couple of things jump out at you now that were hard to see before. Did everybody see where the dog was originally? Yeah, the dog was on the floor. Now, this was a painting that Marek Kosat got advice from Degas on, so we know there are some changes that were made in this composition. What we know as scientists is there are compositional changes in the material. We know these blue cheers in the background have something odd about them. There is this reddish color, and then there is the loss of it in this armchair here in the high part. So we know that this was extended upwards. This was painted in using a different set of materials than these guys. Maybe it's hard to see, but the gaze of the girl has changed. And we know that the dog was not originally in this chair. So they're all pieces of information that come out by constructing this false color image. To give more information to the curator as to possible ways that Degas may have influenced the changing of this painting. So essentially our goals are beginning to shift, I think you can see. We want to determine if the changes we're seeing in the infrared are just initial drawings, or are they partially completed paintings? Or are they finished paintings which have basically been covered over or abandoned by the artist? And essentially this means we need to go beyond just taking good pictures to actually having some ability to map and to identify the pigments that are being used in the composition. And now I'm going to switch the talk over to my colleague, Kate Dooley.
Artists use many pigments, and a lot of them are minerals. And so in this example here, this is an illuminated manuscript, Christ in Majesty with 12 Apostles. And there's many different pigments used in this composition. So this yellow robe of this gentleman here is a yellow ochre, goethite, which is an iron oxide hydroxide. There's ultramarine, used in some of the blue shadows of Christ's robe. And ultramarine is a sodium aluminum silicate that contains sulfur. Red lead, a lead oxide, is used for some of the red robes of the apostles. There's also red ochre present, which is hematite, which is an iron oxide. So that's used for some of the hair. And then azurite is used for the floor, and azurite is this blue mineral. It's a copper carbonate hydroxide. So NASA is also interested in identifying minerals, particularly on the surface of Mars. So they have tools to do that with their Mars rovers. They have different technology. So one thing they have is multispectral imaging with their PanCam system. So they have a detector that they use with different filters, which I'll talk about. And then they have an X-ray spectrometer. And then they also use a Mars Reconnaissance Orbiter where they can do hyperspectral imaging, which I'll explain here in a minute. But they're also interested in identifying minerals on the surface of Mars. So we use, so here's an example of their spectral imaging they can do with their PanCam. So this is a false color image here, and you can see these spherical particles here that appear blue, these blueberries. And these are these like spherical accretions they know are minerals that formed in a wet environment. So particularly hematite, they know formed in a wet environment. And they can identify hematite by looking at how the reflected light intensity varies with wavelength. So they use a detector with different filters, and then these large black circles you see here are their data points from their PanCam. So this is a plot of the reflected light intensity versus wavelength. And just to orient yourself to these plots, wherever you see a dip in this curve is where you have a lower amount of reflected light intensity. And alternatively, you can think of that there's absorption of the light there. And these absorption features you can use to actually do identification of the materials that are present. So we use very similar spectral imaging techniques at the gallery as the PanCam. So for example, this is a cutting from an illuminated manuscript. This is The Praying Prophet by Lorenzo Monaco. And this is an example of our multispectral imaging system at the gallery. So we have a detector, it's a silicon CCD, and then we have an imaging lens, and then we have a filter wheel on the front of this that we can rotate and put different filters in front of our camera that pass different wavelengths of light. So here, for example, this is an image of the painting where we used a 400 nanometer bandpass filter, and this is what you see. And so this is a monochrome image, and you're seeing contrast based on differences in the reflected light intensity. So your darker areas like this reflect less light than your brighter areas. So you can rotate and use different filters in front of that camera, and you can see how the reflected light intensity is changing with wavelength. And so what you end up with is you end up with this stack of images. And so you have this stack of images, and they correspond with different spectral bands because we've used different filters to pass different wavelengths of light. So one thing that you can do, the other important thing when you're taking these spectral images like this, we include these black and white standards you see here. They're reflectance standards, so they have known they reflect light in a known way. And so it's important that you calibrate all your images to these same standards. Because the filters that you use, they can have different transmission properties of light. But if they're all calibrated to these same reflectance standards, then you can actually really start comparing how the reflected light intensity varies in these different images. So that is what that is depicting, calibrating our images to reflectance. So then what you can do, say you can look at, there's a pixel here in this blue leaf. So now what I can do is see how the reflected light intensity varies in each of my spectral bands. So the yellow rectangle you see here is, it's 40 nanometers in width, because that's the width of my bandpass of my filter. It's passing light, it's centered at 400 nanometers, so it's passing light from around 380 nanometers to 420 nanometers. So then you can look at this pixel, you can see the average reflected light intensity in this spectral band, and then you can plot it here. So you can do the same thing, you can look at the same pixel in all of these images, and now you can plot how the reflected light intensity varies with wavelength. So then you can, it kind of looks like connect the dots, but now you start seeing a reflectance spectrum. So that's just a plot of the reflected light intensity versus wavelength. And you can certainly, when you have data like this, you can certainly start separating materials. And for some materials that have simple reflectance spectra like this, you can start to do identification. So this blue pigment here, there's a low amount of reflected light intensity centered at 600 nanometers. So there's absorption of the light here. And this is actually indicative of ultramarine. It has a very intense absorption at 600 nanometers. So from this, we can actually start to identify the materials. So with a data set like this, we have a stack of images, so we can look at the data as images, but you can also drill through your stack of images and look at reflectance spectra. So you can look at images or spectra. And then once you have the spectra, you can actually start doing material identification. So NASA does this with their PanCam system. So they've identified goethite, which is this iron oxide hydroxide right here, and that's this spectrum here. So the data from their PanCam images are represented by these large black circles here. And based on where the light is reflected or absorbed, they can actually identify goethite. So we've done the same thing with our imaging system at the gallery, with our detector, and then our filter wheel. And this spectrum you see here is goethite. And so it was actually used for these yellow or brown robes of some of the apostles. So hopefully it's a little clearer now how the PanCam works and how multispectral imaging works. But with paintings, we expect to see a wider variety of minerals and different pigments within paintings than you'd expect to find on the surface of Mars. So we expect to have more spectral diversity that we're going to want to identify in a work of art. So doing multispectral imaging where you just sample every 50 nanometers or so might not cut it to identify all of these pigments. So one thing you might want to do is actually start doing, this is an imaging spectrometer that NASA uses, and you might want to start doing spectroscopy where you can have, instead of sampling every 50 nanometers, you sample every 3 nanometers or so, and you can reproduce curves that look like this and look more continuous and less like the connect the dots. And that's important because some minerals have very sharp absorption features. So jarosite here in the near infrared, this dip in reflectance is where there's an absorption feature, and some of these are very narrow. And if you were only doing multispectral imaging and only collecting data every 50 nanometers, you wouldn't be able to resolve features like this. So that's why we want to start doing spectroscopy. So spectroscopy in general is just the study of light as a function of wavelength. So we're looking at diffuse reflectance spectroscopy. So we're looking at light that is reflected from a work of art as a function of wavelength. So John went through this example of how the absorption and scattering processes happen within a paint layer. And here I'm showing some reflectance spectra for 4 different blue pigments in an oil binder. So this is the plot of the reflected light intensity on your y-axis versus wavelength. And right here, I'm only plotting light from 400 to 700 nanometers, which is in the visible spectral range that your own eyes are sensitive to. So all 4 of these pigments are blue. And you can see that they look relatively similar because they're blue if you just look in the visible spectral range. However, if you extend out into the near infrared, so beyond the visible, you can start seeing that you see differences here. And so these differences and these absorption features you can use to do material identification. So this is a plot of two different pigments. And in the visible spectral region, which is shaded this kind of blue color, what you see, the absorption features are due to electronic transitions. So within a molecule, if you absorb visible light, it's energetic enough to actually promote an electron to an excited state. And so that gives rise to these electronic transitions. And electronic transitions you usually see in the ultraviolet or the visible spectral region. And in minerals, electronic transitions are what give rise to the color of materials. So for example, like this dashed spectrum you see here, it absorbs light at the blue wavelengths, the orange, the green wavelengths, and then there's a sharp increase in reflectance around 600 nanometers. So this material is actually vermilion. It's reflecting light at a red wavelength, so this appears red. This pigment is red. So, and then in the near infrared, what you're seeing are vibrational transitions. So this has to do with the motions of the molecules that are present. So you can get absorption of the light, like where there's a dip in this curve, that are due to vibrational transitions. So again, we're working in the part of the electromagnetic spectrum where it's visible light, what your eyes are sensitive to, and then just beyond into the near infrared. So as an example, this is a unit cell of azurite, which is a copper carbonate hydroxide. And so this here is a reflectance spectrum of azurite paint. So in the visible, there's a strong absorption you see here. So this is due to an electronic transition that's causing this absorption of the light. But the blue wavelengths right here are reflected. So azurite is a blue pigment because it's reflecting blue light here. But when you get on into the near infrared, these are actually due to vibrational transitions. And there's an example of vibrational transitions at the bottom of this slide here. So you get vibrational transitions when you absorb light in the near infrared or in the mid infrared, which is even farther out. So this is an example of a CH2 group in a molecule. The absorption of light can induce stretching vibrations, which involve a change in the bond length. And you can also have bending vibrations, like down here, where they're involving a change in the bond angle. So these absorption features you see here, this doublet around 2300 nanometers, are actually due to absorption of the light and stretching and bending modes of the hydroxyl groups in the azurite and also the carbonate groups. And then this absorption feature you see here around 1500 nanometers are actually due to stretching modes of your hydroxyl molecule. So this is how, knowing what these absorption features are due to, you can do material identification. So that's a bit about spectroscopy. So now we want to do spectroscopic imaging. So the equipment is a little different than if we were just to do multispectral imaging where we have a detector and then we put a filter in front. So we have a detector, and this time we're using a spectrometer that has a grating, and this grating takes the incoming reflected light and separates it into the component wavelengths. And this grating actually allows a much finer spectral sampling. So the width of our spectral bands is somewhere on the order of 3 nanometers. So rather than with the multispectral imaging, we're passing light in 40 nanometer gaps, we can use slightly different equipment and get finer spectral sampling. So when you do that, what you end up with is this 3-dimensional data cube. So two of your dimensions are your spatial dimensions of your artwork, and then your third dimension is your spectral dimension. So again, this data cube is a stack of images, but rather than just 10 images or so, like we had with our multispectral system, now we have a stack of hundreds of images, and they're more closely spaced together. So, again, like what we did with the multispectral system, if you look at this pixel in this blue region of the Harlequin musician in his face, and then you plot in your first image, if you look at that same pixel, you can plot the average reflected light intensity in this spectral band. But this time, the spectral band is very narrow. It's about 3 nanometers in width, as opposed to 40 nanometers that we had with the filters that we use for our multispectral system. And then what you can do is you can drill through your stack of images and you can plot how the reflected light intensity varies with wavelength. And you can see, because we have hundreds of spectral bands, and because they're very narrow, our spectral sampling is much higher, and then this spectrum now essentially looks continuous. It's less connect the dots like now, and it essentially looks continuous. So based on these absorption features you see here and here, this lets us know that this paint contains cobalt blue. And because we have higher spectral resolution, we can actually, you see these slight wiggles in this absorption trough here and right here. Because we have the higher spectral resolution, we can actually start identifying some of these absorption features, and so we can distinguish that. So now this is reflectance imaging spectroscopy, which is a type of hyperspectral imaging. So now we're collecting hundreds of images as opposed to the 10 or 20 images we were getting with multispectral imaging. So again, you can look at your data, you can look at all the images that you've collected, or you can look at the spectra that you can extract from your data cube. So now we'll move on and talk about how we use some of this technology to look at works of art. So we have 6 examples we'll talk about, and I'll talk about the first 3 here and then hand it back over to John, and he'll walk through the last few examples. So as John showed before, this is the Feast of the Gods. So it was the Duke of Ferrara commissioned this, and Giovanni Bellini painted this initial composition with this. These trees span the width of the canvas before. And then the Duke commissioned a couple of reworkings of this painting. And so ultimately, Titian made the last reworking where he painted this mountainous backdrop that we see today. So this is what this image looks like in the near infrared. You can see this. And there was a lot of work done on this painting in the 80s where they had taken cross sections, which are very, very small components of the paint, so on a microscopic scale. And so they took cross sections and they identified a lot of the pigments that were used in the painting. So there was a cross section taken from this existing hill background here. And so this is shown here at the bottom. And you can see in some of these lower layers, there's this layer, and you can see some of these blue particles. And using microscopy, which is when you're looking at this paint sample underneath a microscope, they could identify that this was azurite. So these blue particles are azurite. And then this layer also contained some lake pigment. And then this was, on top of that layer, is this green glaze, which was a copper resonate with azurite and a red lake. And then this final layer, what we see is this brilliant green-colored layer. So we knew that there was azurite and some of these intermediate layers in this point on the hillside. So we thought, what else can we learn with these imaging spectroscopy methods that we've talked about? Can we bring some additional information to the table? So here is a false color infrared image. So I've taken the spectral band images at these specific wavelengths and placed them into the red, green, and blue color channel. So you can see now, so this is the region between Pan and this nymph with a blue bowl. And you can see here the delineation of this hillside. You can see this hillside now is appearing as this blue color. And you can see, if you look closely, the brush strokes that are associated with this intermediate layer. Because we know these brush strokes don't correspond with like what you see on the surface. So now we're seeing, which is really pretty cool, the brush strokes of this intermediate hillside layer. And now if we look at some spectra, some reflectance spectra from this region. So just so this blue bowl is representing like a Chinese porcelain, and it has this blue painted pattern on the surface. So if we look at a spectrum from this blue area, this is what we get. And so this is actually indicative of the pigment azurite. So if you remember on the slides before, it had this strong absorption doublet around 2300 nanometers that are related to the hydroxyl and the carbonate groups. And then it has an absorption feature around 1500 nanometers related to the hydroxyl group. So we know the blue pigment on the bowl is azurite. So now I wanted to look at the pigment in this hillside where we see these brush strokes. And you can see here in this red spectrum here, we see an absorption feature at 1500 nanometers. That's very similar. This absorption doublet you see here is actually due to the oil paint, because this is painted with oil. So that's what these doublets are due to. But if you look here, this absorption feature looks slightly more broadened, because I'm getting some contribution from azurite. And just for comparison, if you look above the hillside where there actually isn't any azurite, you don't see this absorption feature here, and this feature you can see looks a bit sharper. So what's cool about this is with the imaging now, based on the spectra, we know that this material here in this hillside contains azurite. And now we're able to map its distribution because we can see this azurite, we can see the layer that contains azurite, we can see these brush strokes. So this is adding something because before we just knew there was azurite in a single cross-section taken, but now we can actually map the distribution with the imaging spectroscopy, and then we can identify what this material is by looking at the spectrum. Okay, so the next example, this is a panel painting, an early Renaissance panel painting by Cosimo Tura. And this is the Annunciation with St. Francis and then St. Louis of Toulouse. And so there's also a panel of Mary here and then Gabriel. So one of the things that we can do, since we're able to extract spectra from our imaging cube, and we can actually do material identification. So we have algorithms that we can use to actually pull out spectra that represent materials in this image. So that's what we've plotted here. And then we've created this map here in the center. So we know from the spectra, we know, like, for example, azurite, this light blue spectrum is used in the background in the sky. We know that her blue robe is ultramarine. The red robe you see here is actually an insect-based red lake. So there's insect-based red lakes, there's plant-based red lakes. So as John likes to say, this is a non-vegan friendly. And you can see this is the yellow, this scattered distribution is where there were paint losses. So this is actually, this material is due to cobalt blue, which has a very distinctive spectrum. And you can see its scattered distribution, and that maps out nicely. So one of the things that we weren't quite sure of with the reflectance imaging spectroscopy was the landscape. So right here. So the systematic catalog entry for this painting describes the landscape as being this fantastic rocky landscape. And based on the spectra, we thought that this looks similar to umber. And umber is an iron oxide with manganese oxide. And this looks similar to like reference spectra we have of umbers. So we thought, okay, if this is umber, let's look for iron and manganese. So this is just, for an example, a unit cell of an iron oxide. And so this consists of atoms of iron. So we have another technique that we use to look for iron and manganese atoms that come from a particular element. And so that technique is X-ray fluorescence. And now we're talking about using X-rays as our excitation source. So we're using energy that's more energetic down here. And so with X-ray fluorescence, what you're doing in this little diagram of an atom, you're actually using X-rays, and they're energetic enough that they kick out an electron that's orbiting in one of these inner shells. And when that happens, you can get an electron from an outer shell, fall back down to take its place. And there's a difference in energy between the inner and the outer shell. So when it does that, this electron that's falling back down to take its place actually has to release some energy, and it does that in the form of a secondary X-ray. And that's what we detect. So the energy of that emission is related to the element or the atom from which it came from. So with X-ray fluorescence, you end up with a spectrum that looks like this. It's a series of peaks. This is your X-ray fluorescence intensity on your y-axis versus energy. And so, like, for example, this peak here resides around 6.4 electron volts. And so that's the energy where if you have iron present, you'll see a peak in your spectrum at that point. So you can get information about what atoms are present, and they come from which elements with X-ray fluorescence. And we can do X-ray fluorescence imaging spectroscopy by raster scanning our painting. So we can We have our excitation source and our X-ray detector, and then we can move the painting and collect an XRF spectrum point by point. So that's how we build up an XRF image. So in this question about what is the landscape, we wanted to look for iron. And so here's this map of iron you see here, but you can see in the region of the background, I really don't see a whole lot of iron. However, when you look at the copper map, you're actually seeing a lot of iron in the background. We know there's, a lot of copper in the background. We know there's copper in the sky because there's azurite there. But then we see copper in the background. And some of the intensity differences you're seeing in this copper map are mimicking the types of shadowing you're seeing in the visible. So this really clued us into the fact that this is actually a copper-containing pigment in the background. So rather than being this fantastic rocky landscape, this was likely actually green at some point. And so this really clued us in that this was probably a copper resonate that's degraded. And with the panel of Mary here, here's a false color image from the near infrared. And from an image like this, you can kind of start seeing some of the underdrawing that's used, and you can kind of see some of the hatching that's used for shading and modeling of the robe. And when you look at spectra, if you look at a spectrum that's collected over one of these underdrawing lines, it looks like this. And this is from a region free of restoration that was just over the blue robe, not over an underdrawing line. So you can see there's a relative difference in reflected light intensity, but this region here is also a little more absorbing here as opposed to this. So we thought, based on the spectra here, we thought maybe the underdrawing was an umber. So what we can do is look at this spectrum here, taken from over one of these underdrawing lines, and we can use an algorithm to actually find the degree of match between this spectrum and all the pixels in our image. And when you do that, you get something like this. So this is this map, where in this map we think the dark lines are actually corresponding to original underdrawing. So you can see some of this hatching and shading used here. And in this region, we know there's some restoration in this regions of the folds here. We can actually see below that now and see what some of these presumably original underdrawing lines look like. So if we jump forward a few hundred years and talk about abstract expressionism, we'll talk about Jackson Pollock. And so we had imaged a section of Lavender Mist, which is in the collection of the gallery. And Jackson Pollock, he's probably most well known for these drip paintings like this. And the way he created those is he would lay the canvas on the floor, and then he would fling paint onto the canvas with brushes or with sticks. So it was a very physical process. So he used paints that had different binding media. So that's what is of interest in this discussion here. So for example, so here's Lavender Mist on our easel. Here's a reference spectrum of oil, and here is a reference spectrum of alkyd resin. So with oil, this is just shorthand notation. These long chains you see here are hydrocarbon chains, where there's carbons and then there's hydrogens coming off of them. And that gives rise to some absorption features from the CH2 groups in these hydrocarbon chains. So you get this doublet right here that's due to stretching and bending vibrations of the CH2 groups. And then you also have an absorption feature here due to stretching of the CH2 groups. So with alkyd resin, it's an oil-modified polyester. So it has some hydrocarbon chains you can see here, so it shares the same spectral features as oil. So it's got an absorption doublet here, this doublet here, but it also has some additional spectral features related to this aromatic ring structure that you see here. So you can get stretching due to the aromatic CC and CH stretching that gives rise to this more intense absorption right here, And then you also see this shoulder that appears at lower wave numbers relative to the oil. So when we look at a couple different white pigments in this painting, here's one white pigment, and it looks very similar to the spectrum of oil. If we look at another white pigment, you can see this absorption feature here. You can see the shoulder appearing here. This looks more like our reference spectra of alkyd resin. So one thing that we did, the differences when you look at the reflectance spectra are relatively subtle between these. You see the shoulder, but if you actually calculate the first derivative with respect to wavelength, these differences you see in reflectance become accentuated. So the shoulder here that you see actually becomes like another peak in your first derivative spectra. So we actually use the first derivative spectra to actually make material maps of the binding media. So here's this about a square meter of the region that we imaged. Here's this map. This maps to oil. So you can see that you have these, this maps to more or less like these white skeins of paint that are more or less straight. And they're kind of like these tadpole shapes where you have probably him squeezing paint from a tube where this is the initial squeeze that results in this head of the tadpole, and then this extended squeeze that results in this long tail. Here's the map that we get for alkyd. It maps to color paint of different colors, so there's white and blue and different colors. But you can see some of these paint strokes are more curved, which suggests that the paint is more fluid, and you can see that its distribution is more scattered, so it's likely underneath other layers of paint. And this is something that looks kind of like a mixture or layering of the two. If you look just at this detail here, you can see this white stroke and this white stroke look very similar by eye, but this one is actually oil, and some of these other strokes, like here, actually map to alkyd. So using the spectral properties, we can actually distinguish between different binding media that he used. So with that, I'll turn it back over to John, and he can walk through the rest of these examples.
All right, so we're going to go back in time, and we're going to talk about a choir book, basically that was constructed in Florence, and was constructed by two different groups. One was a workshop by Pacino, and the other one was a workshop by the Master Dominican Effigies. We don't know anything more about him than that. So we're looking at something in around 1340-ish time frame. Now these Lodaro's choir books were relatively large and were commissioned by wealthy tradespeople in Florence. They were put together and they would have celebrations for different parts of the year. And they would be taken around to different places or holy sites, and these tradesmen would go and chant, and this would be carried by a priest. Now, this would not be tied to a specific church, but it would be tied very closely to these wealthy groups who had them painted. And of course, they went for the best materials and put out the best money, so this would be only of the highest quality. Now, of this particular Lodario, there are only about 28 leaves that remain. There were probably 120 to begin with. And they're basically written in the Italian vernacular and not in Latin, so that actually the tradespeople or the people that had them created could follow along and read them. When Napoleon came into Italy, he essentially disbanded and shut down the church, and these pages and books were sort of scattered. And some of them sort of got cut and then migrated to different parts of the world. We have some of the collection here at the gallery, although some of the books still remain in Europe. This particular book was completely disassembled. So we have 3 pages here that we're interested in studying. One of them in particular is this one attributed to Pacino, which is involving Christ with the apostles. So Christ in majesty with the apostles around. We talked about it earlier briefly. Now this is another cutting here. This is a illumination by the mass for the Dominican effigies, and you actually can see not only the inner portion, but all of the marginalia and the writing around it. Now that's not even a full page. A full page would look like this. So you can see that this has been even trimmed down further. Now, one of the things we wanted to do was to study the materials used in all of these illuminations that we have, these cuttings, and our colleagues at the Getty studied theirs as well, to see if we could learn about the working methods of these two different workshops. So this is a setup here showing a hyperspectral reflectance camera that we built here at the gallery with a grant from the National Science Foundation and the illumination under examination. And we collected 750 images to collect a spectral database to interrogate. And from that, we pulled out the reflectance spectra of blues. And you can see there are essentially three different blues here. We know they're blue, they're high reflectance here, but there's a shoulder and these features here. And as Kate indicated earlier, it's not a surprise that this is azurite, and up here is natural ultramarine, and this is something in between, ultramarine layered on azurite. Azurite's a very cheap pigment, ultramarine is a very expensive pigment. So having this data, we can go back and interrogate the data set, the data cube, and make a map and find out where these illuminators decide to use the azurite and the ultramarine. And you notice the azurite's used extensively throughout the blue regions of the illumination. But right around Christ, we see the reddish color, where there's natural ultramarine right on top, and actually on his white robe is where we find this very precious ultramarine right around Christ. Makes sense. It is interesting that it's also found around here on John, but that's probably another story. One of the questions that came up in the analysis was, since our page is cut down and we just have the central illumination and not the writing around it, is where does it go in the Ladaro? Where in the book does it go? And it would be really nice if we had some writing. I kind of skipped over this, but our cutting is not only cut down so there's no writing around it, it got mounted onto a board, so we can't see what's on the back. And on the back there should be some writing and music. So it's been postulated that it could be the frontispiece. It could be at the end of the book. There are various places where people think it could be. Without the additional information accompanying text, the placement of the book is uncertain. So we thought maybe we could try to get at this by using our spectral imaging methods. And just to give you a scale of the size of these books, they have to be read by people without glasses from a bit of a distance. So they are relatively huge. Well, we noticed in the infrared images, the false color infrared images taken, that we could start to see some text. And that was pretty exciting. So doing a little bit of math, in this case principal component analysis, we were pretty excited because we could start to actually see letters. So, okay, this is great. We're going to send this off to the people who can read Latin and early Italian, and they're going to tell us what it is, and bango, everything's fine. We sent the images off, and they sent us an email back saying, really exciting. Could you get a bigger, better image? So, well, okay. What's happening here is the light scattering by the paper is obviously limiting the readability because the light's going through the paper and then reflecting back off the white background and out. So we said, okay, why don't we scan this with our atomic elemental scanning system? This is a setup here. And our hypothesis is these hymns are written in iron gall ink. Notice the word iron. For me as a physicist, we should be looking for iron and then maybe some of the trace elements like zinc. So we'll go do some mapping. In about, 3 days later, we start to get these maps. Here's the map of iron. Doesn't show any writing. Here's the map of zinc. It doesn't show any writing. It matches the azurite. And azurite and zinc is not in azurite. It's actually a trace element. And that tells us a little bit about the mine where it comes from. But it's not answering the question. If we look at mercury, which is related to vermilion, which is a pigment obviously used for vermilion, we can see the music lines on the back. But we also see this little bit of a design here, which was kind of exciting because that design, when you look at it, we actually took an image with an X-ray setup. We can actually see at low voltages the design pattern, which I colored in Photoshop using the tools that my daughter taught me how to use. And you can see this design is pretty intricate. And you see these at the starts of sections of words. So we know there should be wording across here. We've seen the wording in the infrared. But in the hyperspectral, we're just not reading it. So then we had another idea. What if we flip it over and read it from the back? And it worked. So now we're actually, and this is lead of all things, we're actually seeing in lead, we're seeing the contrast to make out some letters. And they're sharp and they're clear. And this, thank God, the art historian said they could read. That's what it translates to in early Italian. This is kind of what it means in English. The word made flesh, which holds up the ceiling, altar with. So it's a beginning of information. The good news is this fragment of chant is written in Italian vernacular and not in Latin. So that means it's definitely part of such a choir book. And it kind of suggests that it's coming from near the end of the book. But we really would like to have some more of this text because anybody who reads Latin knows that context matters and we need a few more words. So we have some more image processing to do. So we'll turn back now to this particular painting that's fascinated me for a long time, this Blue Period painting by Picasso, Les Gourmets. And this picture of the woman underneath. And again, as we mentioned earlier, this particular, what appears to be a drawing of a woman underneath is very intriguing, but the question is it related to a finished painting, or is it even by Picasso, and when did he do it? And that just begs more information. With a hyperspectral imaging, we can go from this to a more isolated image of the woman, which is a lot clearer to see, and we begin to notice that she has a necklace, which is interesting because, as I understand it, Picasso did not use much jewelry when he did painting. Well, he did not paint people with jewelry, I should say. So we said, okay, let's try to look at this with the elemental scanning system. We know that from the X-ray, there's some X-ray absorbing material, probably lead white, quite a bit of it, because it's very hard to see the face. So let's scan for lead. And there they are, lead alpha line and alpha and beta. And we don't see the woman. And this actually has to do with the fact that there's actually zinc white on top, which is preventing seeing the lead. So we kind of ran into a wall. But then we went back to the hyperspectral data set and said, well, what if we measure the depth of the hydroxyl band that is characteristic of hydrocerussite, in this case, lead white with the presence of the hydroxyl bands. And when we do that, we get this image. And I think I can probably convince everybody in the audience, this looks like a painting. This looks more three-dimensional, and you can see this cross is showing up, which tells us this is a woman with a mantella who is either going to or coming from Mass. So that's a lot more information. What we did get out of the elemental scanning was the presence of chrome. And that chrome maps into places on the final composition, but that necklace we talked about, and a little bit associated with the cross. Well, that would be very convenient if that was chrome yellow. Unfortunately, with elemental imaging, we get some of the atoms. We don't get enough to tell us the pigment, but we can infer it. So chrome yellow makes sense. And then we spoke to a curator, art historian in Barcelona, who made us aware of this particular painting by Picasso. Happens to be 1901, very similar to the dating of the Blue Period painting that we, Les Gourmets. So if you'll take some license by a bunch of scientists with some Photoshop minimal skills, maybe we're looking at something like this. Okay? So it's not drawn, it's painted, we know where it goes, and this apparently shifts the date of our painting a little bit. Okay, well this is the last example we'll give you. It's kind of an exciting example because at the end you'll see there's a show coming up related to this particular subject. This is a painting by Fragonard, It's associated with a fantasy series. These are a series of paintings that you'll see in a moment that were only associated together by grouping them by their style, okay, and not by anything else. And it's a beautiful picture of a woman reading this book. It's a very quiet scene. And it's a favorite in the gallery. Now, if you look at these paintings that are in the fantasy series, for sure, you notice there is a distinct difference between these two sets of compositions. All of these are in fancy costume, Spanish costume, well, she is too, but they're all sort of engaging the audience somehow. They're all looking out. They're not in this sort of quiet view. They look more like portraits. And this has always been sort of an issue with this painting in terms of how it relates to this group that is notionally, again, associated as these fantasy figures based on the style. So we were asked to relook at some of the clues that people had noticed over the years. One was, if you start to look behind the woman's hair, there's something going on here. There's sort of gray paint, and there's a faint characterization of some sort of clouded material here, maybe a feather. And if you equalize the histogram, if you take the image and stretch it and make sure each gray level or color level has its own level of importance, you can see clearly he painted out what is essentially a feather, not unlike some of the feathers we saw in the hair of some of the other members of the fantasy figures. So that's one clue, sort of a pentamente. The other clue is the X-ray. The X-ray shows a second head, an earlier version of this painting with a person looking out at us. That's certainly much more convincing. And this is a close-up of the same thing. The challenge with such images that they tell you something about where the person's sitting prior and where they're looking, it's really hard to assign gender on the basis of this, or age. It's just the nature of X-rays. So we were asked to see if we could do a little more to pin it down. So how did the figure really look? Well, we did the hyperspectral imaging scans and made a false color image. And now you start to look here, and maybe we'll take a minute to stare. You see the woman's face and profile disappearing. You can see the lips of a woman underneath. You can see she has a black tie around her neck. That straightens out the gender. And you can see her forehead, and you can see one eye and a little bit of the other eye. We do have a lot of other material that's absorbing in the IR, making it hard to see the rest. But the only change that's been made in this composition, except for someone doing that, is essentially that of the face. So it's definitely a woman, and she's looking out to the group. But we have the elemental information that we could get by X-ray fluorescence to sort of flesh this out, to get more information about the pigments and maybe get a better idea of how to reconstruct the earlier picture. But we can look at lead, and you can clearly see more of the figure. She looks rather old here, doesn't she? It looks rather young here. We can look at the iron, which gives us more information about this extension or whatever was a costume part attached to her hair. And then we can look at the vermilion map, which is basically associated then through the mercury. And now you can see the ear that we can't see in the hyperspectral imaging. And you can see she has red in her hair, so maybe she was a redhead. And then, of course, we have this piece of information. So now we have enough pieces of information to give it back to the conservators, especially someone inclined to actually do some simulation and painting. And also we have the collection of other fantasy figures to draw from to understand things like possibly these little dots here of color, which were probably jewels along with this feather. And when you do that, that's what you end up with. So we went from possibly a guy to this. A woman fits in with the series, and it makes a much more compelling story. There's more to this story. If you come to the exhibit, you'll learn a lot more about how these are more closely related. We did extensive studies on a whole series of these fantasy figure characters. These will be in the show, and there's a drawing that popped up that sort of links some of these together. And that brings us to the end of our talk today, which we have thoroughly enjoyed. And there are a lot of people to thank. We would really like to thank our colleagues. This work is not done without working closely with conservators and curators who come up with ideas, help direct the research, and actually tell us what we're looking at, since we're all scientists. And also our colleagues in the scientific group here at the gallery who are first rate, who know a lot about different pieces of information that can help ensure that we're moving in the right direction as we develop these new techniques. And we're indebted to a lot of different funding foundations, Samuel Kress, the Mellon Foundation, as well as the gallery and the National Science Foundation. So with that, we close, and thank you very much.